Hello and welcome everyone back to my another video tutorial. So lately I was playing around with my RockRL reinforcement learning library, and in the last video, as you remember, probably you should watch it out if you haven't seen it, but I was training following agent with a simple environment. There was no obstacles. So I decided I need to test further my reinforcement learning agent library to check whether it is possible to train my agent to work on this kind of difficult environment where there's a lot of bits and many obstacles in a way of this agent. So why I decided doing this? Well, there's a lot of tutorials online with bipedal walker that shows you how to train it, but there is a truth that these kind of bipedal walker environments are pretty simple and it's not very hard to teach them to walk. And even when there are some mistakes in logic of in a PPO, for example, training and code or etc., it still might learn to walk. But when we come to this kind of difficult environment, it gets into another level because it's really hard to train this agent to walk or run in an efficient way and produce us good scores. So basically, I decided that, okay, I'll need to make sure that my library works well and my agent might learn to walk. And you might see it, I'm running right now this in a test mode and it works pretty fine and pretty nicely, even though it fails sometimes, but you might see that it is able to jump through these pits or walk through this kind of rectangles and other obstacles. So basically that was the main idea for me to what I need to learn, and I need to teach this agent to do such things. And you might see I'm successful. This means that my PPO reinforcement learning agent in my library works pretty well and I could move on with harder tasks. But it's up to you. You might write in comments if you like it, if you do not, what else I should try to do. And we'll see, maybe I'll implement these things. Have you seen right now how this agent walked out of this pit? That's amazing, because I haven't seen this online. There is few videos that shows you how they learned or teach this agent to walk through the same environment, but I saw that it works pretty damn bad, and there is no such agents that gives you pure code, open source, that you can take out of the box and train your agents to do this. So right now you might see that it finished 10 episodes. So okay, that's fine. I'll upload this agent somewhere on my GitHub page so you could download it and run. But keep in mind that you might need to downgrade your TensorFlow version, because if you're gonna try, for example, after 2 years, there might be TensorFlow increased in version and you might not be able to load older versions that I used to train. So don't worry, I'll include the requirements for this version and you'll be able to use it. So let's move to the code. So I'm showing you right now this test code, and if you were watching my previous tutorials, you already saw it, because I ran my simple environment within the same code. So let's walk through this and let's understand what we are doing here. So I'm using Gymnasium as gym. Keep in mind that you need to have a newest version. These are the requirements. I'm using TensorFlow 2.10, but only because right now I'm on Windows. You might know that it's pretty hard to install GPU support on the later versions of TensorFlow. But I tried this on Ubuntu on Linux, and everything works the same as in my package. So you need to Gymnasium, TensorFlow probability, and of course my RockRL library. That's it. So let's go to the test code. I import a gym, I import a NumPy, TensorFlow, I set the GPU memory grow, not to reserve all the GPU memory of my GPU, and then I import some stuff. So this is vectorized environment and memory manager. So this vectorized environment is, well, kind of special my implemented object that handles 4 or way more environments simultaneously in the backend. So, well, I implemented this because it will take insane amount of time if we train our agent with one runner. So to train it, I used to, I don't know, 128 simultaneous environments, and I was able to save a lot of time. So basically, I'm doing the same while running the test. You might see that there was 4 environments because I am simply set here as 4 environments. And so we create the environment in a way like this, and I render mode as human, and only because I want to display you the results, how it runs. So then I receive the action space and input shape the same way as before. I'm loading my saved model. I'll include this somewhere else because it's right now in my runs, but I don't want to push this into GitHub, so I'll maybe add somewhere here between the bones. So change the link, or I will change this for you. So great. Next, we can move with memory manager. That's another very simple object, but simply to track our memory of each environment. Because for example, second worker might crash after 1000 episodes, and my first worker might crash after finishing everything. And we don't want to reset all environments, but we want to track which environment crashed and reset only that one and return back to the loop. So great, we then call the states environment reset. We receive the first state and info that we are not using. I'll run this for 100 episodes, and I'm tracking how many episodes it finished. And I track the average score. So what I do here, I do actual predict on states and I receive probabilities. And that's, I split these actions into sigma from probabilities. And if you would like to know what this means, we need to go into the training code, what we will do after we finish this one. But it won't take a lot of time. So let's continue. So I'm running the step on the actions that I received from my model, and I receive next states. I save this stuff into the memory and I move on. And then I'm iterating over and then simply checking whether in my memory there is some environments that achieved done state. And done state is simple whether my terminated or truncated step was achieved and returned as true. But this way I'll receive an index of my environment or an empty dictionary. And if I receive empty dictionary, I don't need to do anything, but otherwise, if I receive any index, I need to reset this environment, save the score, print the score as I'm doing, and reset the memory. That's it. So I'm iterating over and over, and here you can see I'm receiving the results. And there at the end is my average score through all the environments. Right now it finished 30 episodes for 31, and I'm simply meaning the score to know how well my runners are running. Great. And let's go to my another training code. And if you would like to run the training code, you need to open this code and simply install all the requirements, and you are good to go. So what I'm doing here, simply the same as before, importing gym, importing Keras models, vectorized environment, and here differently from before, I'm importing the PPO agent. Well, that's the same agent as from my previous tutorial. Then I'm creating these kind of very simple actor and creating models that we are training. As you might see, there are only 3 layers of dense layers and two heads. So 2 heads, what does it mean? So actions, we need to know what are the action space in our environment. So we are predicting this, but also we need to have a sigma. And what is sigma? And sigma is responsible for exploration and exploitation stuff in our environment. And model is learning to walk by minimizing the sigma. While sigma is increasing, it adds some randomness into environment, and it's harder to learn, or it learns to, for example, walk through these obstacles or pits. So we'll come to this later in TensorBoard. So then I concatenate these two actions in sigma, and this is the reason why I need to split actions and sigma, probabilities and sigma, when I'm receiving some results, when I'm predicting. And we'll come to this. And here's another critic model, and it's very simple. We receive the value of 1, and lastly is dense of 1. That's pretty simple. And what we do next, so here I initialize this environment in this hardcore bipedal walker. I use 128 simultaneous environments, workers that are running in background. That's great. So I create these environments, I receive what is the action space and input shapes of my environment, and then I create this agent. So I create the actor and critic, and then I use Adam Optimizer of this pretty low learning rate. But I'll talk about this later when we come to the my TensorBoard results. And I use continuous action space. If you don't know what it is, so you need to check my previous tutorial, that's a simple bipedal walker environment. So I train it for 10 epochs, and I use KL coefficient of 0.5, C2 of over 1, lambda, gamma. That's pretty standard hyperparameters, but keep in mind that they are very sensitive to training stuff, especially the harder environment, the more sensitive these kind of hyperparameters might be. So now, next I create this memory. I use memory manager to create memories for my 128 workers. So this is why I'm using num environments argument here. And it simply manages memories there, what I have. So next I use mean average. This simply for saving and the best scores of my model, so I could at least save the best model that is training right now live. And I simply run this through while loop, and it simply here start training my model. Okay, now that's pretty different from before, but my agent has a special act function that I give a states, and if it's training, it performs these states in one way, and if it's in a test mode, it works another way. So I run do everything the same way as in a test. I run these actions on the step. I receive the states, I save these states into the memory. Keep in mind that I receive states for all 128 environments at one step. So my memory manager handles all this stuff. And as before, I'm checking whether my environment terminated, truncated, finished, and etc., and check the index of this environment. So I would know which memory I need to reset, which environment to reset, and which environment made me the best scores. And I mean these scores, and here I simply save the model. And if I go to my save model, there is if there is a path, it says my actor and critic models there. That's nothing special. And that's it. I print the results over through all training loop, and everything works just pretty amazing. And that's it about this. And main magic is behind this PPO agent object. And if we walk inside of it, there is a lot of hyperparameters that you might change. And I try to add comments and documentation for all these arguments, so you would know what they mean and what you might need to change or not when you are implementing this on your own. And what here happens, I save configurations. This means that I save the hyperparameters somewhere along the model when it's saving. And if I open my model, there is config YAML, and you might see that I saved the hyperparameters that I use for this training. And I'm doing this because if you're familiar with reinforcement learning, sometimes it's really hard to train these agents. And we are trying to change these hyperparameters. And when we successfully train our agent, we are not sure what hyperparameters we used. So then we continue changing these hyperparameters, but suddenly we receive bad results. And we want to come back to our great results that we received before. But if we don't have saved these, we don't know what they are. We can't remember what we changed or not. So this is the purpose why I'm saving these hyperparameters of my model. Yeah, that's it. And where I was? Oh, I was in this PPO agent. Let's go. So I save the model. I calculate the critical loss if you want to get inside. And this is the two different ways how I calculate log prob from distribution for continuous in discrete environments. This is my debug stuff. I will remove this later. And this is how I calculate the loss. For discrete and continuous, it's a little bit different, but we receive the same results. And I return the loss, entropy, approx, scale divergence, and sigma. So these are the parameters we would like to track while training. This is the action mode. Well, whether we need to use this in discrete and continuous environment and etc. But mainly they won't change a lot, but they might. It depends where you use, so you might also change this if you need. But probably if you are using this library correctly, you might not need to do so. Okay, sorry, I removed something. I calculate advantage reward. And here is a predict chunks function that you might have some questions about it. So what I'm doing here, while we are training, you notice that I'm not doing any predictions on critic model, and there's a reason. I don't want to spend time on each step, do the predictions for critic and saving this on the memory and etc. We don't need this. So basically what I'm doing here, while I'm running the train agent code, I simply call this predict chunks to predict all my critic values. But for example, sometimes we might use environments where we are running it for 1 million episodes, steps in episode, I mean. And if we would try to predict whole 1 million values for critic, we might face some GPU memory issues, and it will fail. So basically, to overcome this problem, I'm predicting simply in chunks. And so on. There is another helper functions that we might use to reduce learning rate, log to writer, custom logger. This is related to tensorboard. It logs everything for us in a tensorboard. We don't need to do this manually. There's a train step wrapper. I'll come to this later. And here it is, their main train step function. And I use, sometimes we want to use shuffle, we don't want to use shuffle, and etc. And what we do here, I simply use the standard ways how we calculate gradients in TensorFlow and etc. So as you might see, I predict the critic values and prob values and etc. But you might see that here is something strange here. Well, I saw that I'm using this on chunks, but I'm not using this on chunks. And here's the reason. There is a train step wrapper that handles all this stuff for us, together with the logging stuff. So let's go to this log wrapper. And this is a decorator. And if you're not familiar with decorator, it might be hard for you to understand. But what this means that when we call our train step function, the data that we put there first comes here, we work with it, and we return same data. So what I'm doing here, there is my train step function that comes together, and you might see that I have here data, and I have trained that data epochs, how many epochs I want to train on it, and etc. And this means that I'm using that for loop And here I have these kind of batch data, and I iterate through my old data through these batches for epochs and etc. And later I add this custom logger, the history I would like. And in this way, this is the logic to handle the batching, logging, and etc. to save efficiency and memory and logging all at once. It might look very complicated at first, but when you look closer to it, you will understand that everything is pretty clear and understandable. And that's it. We simply run this training code and we are good to go. So, but you might ask, okay, I'm training this, so on, show us the results. You saw agent running, okay, but real data scientists never loves to look at this kind of results. Well, they are for fun, to know that everything works. But what we'd like to look at is TensorBoard. So let's open TensorBoard. So here is my RockRL GitHub page. If you would like to, if you have any questions, you can pull the issue, you can pip install RockRL if you would like to use this in other projects and etc. Here is my links to my tutorials that I'm right now recording with the code where delays and etc. So you might get familiar with it. So here is my TensorBoard. So let's refresh it. So let's go to scalars. That's great. And you might see that I have the actor loss, critical loss, and actor loss is increasing. This is also doing something. We're not sure what, but it's doing. And I trained it for 500 epochs. As you might see, it took me 1 day and 9 hours, and another model 1 day and 6 hours. And there's a difference that in one model, for example, if I open, I used different workers, but I don't have it here right now. So I can't show you, but I remember that in a red one, I used 64 workers. In this one, I used 128 workers. And you might see that the difference in time is only 3 hours. So not that huge difference, but it's around 10% when we look at the hours in a speed. So imagine if you would need to train this for a month, so you would save around, I don't know, half a week of training with simply more workers. So there's many ways, I believe, that how we can optimize it, but this is not the goal of my tutorial. So let's look at other more interesting parameters. So what's the difference here between red and blue? Main difference is the learning rate. What I used here, so learning rate. So as you might see on the red, I used a lower learning rate than on the blue, 5 times lower, and there is a huge difference from here. So let's look at the entropy. You might see that my blue agent looked way more stable than the blue one while training. Well, even though that we are looking at the entropy, but it gives us already the results that it was decreasing. That's exactly how our entropy should look like when our model is training and able to train something and learn something. So let's move to another KL divergence, for example. I'll decrease this a little bit. Yeah, so the KL divergence, what it shows. So basically, KL divergence shows that when our agent is training, it gives us the difference previous training step with current step and how much our agent learned, the difference of learned stuff. Well, we measure this in gradients, but we represent this in this way. And mainly my magic stuff in my kind of RockRL library is that I use KL coefficient in a loss to limit it from changing too much. When our agent starts to show some spikes in the scale divergence, this means that it might be this learning something. It means that it's learning into wrong learning path. So in this way, I limit this increase the loss to limit this on bad learning stuff. And you might see that on the red graph, I used higher learning rate than on blue. And you might see that differences in these epochs are different. So I prefer the blue line because it was more stable. So let's move to the loss. Well, talking about loss is in reinforcement learning is really hard, but you know that it started high, started decreasing, and it wiggled a lot. Well, it's nothing a lot to talk. Learning rate, you might see that it's different. Blue used way lower learning rate than a red one, and still it's great. And rewards. Look at rewards. We might see that red agent with a higher learning rate started to learn stuff faster while getting rewards, better rewards earlier. But later, somewhere here, when it started to walk, to understand what is walking, it started to struggle. This means that it was really hard to walk through these obstacles or pits. It was really hard for him to learn what it needs to do. But lastly, it learned it, but it took more time than for our blue agent. And if we look at the sigma, that's kind of crucial. That tells me the randomness. So we might see that at the beginning, first episodes, on first epochs, it was around 50% randomness. This means that half on half. It used 50% exploration, and it did a lot of random stuff. But later, it decreased by decreasing this randomness. And we might see that the red stuff really quickly started to decrease this randomness in our agent, and this gave us the results that it struggled to learn moving through these obstacles, while our blue agent all the time used a little higher this randomness, and it was able to learn faster to move through these obstacles, and it was more stable in learning this stuff. And at the end, you might see that blue line is lower than the red one, and this means that our blue agent was more confident about its steps, and it didn't need that much randomness to improve this exploitation in his environment. And this means that it learned better. And we might see this from reward graph, that almost all the time the blue agent was defeating the red one. And this means that in our case, the lower learning rate was better. And why I'm telling you that we need to play around with this learning, you might see that it took me around 4 hours to understand whether my agent keeps learning or not, and only took 8 hours or 12 hours to understand whether my agent keeps learning to eliminate these obstacles and work through them. And this is the hardest stuff in our reinforcement learning in continuous, that we need to walk through many epochs to know whether it's training or not. And we can't use our GPU 100% because because there's a lot of load on CPU for these environments to handle up, and each step is dependent on the prediction from our agent. So this means that I don't know, a lot of stuff happens on CPU and GPU, and this results as inefficiency in GPU, and we can't do anything about that. Well, there will be solution to move everything, our environments, to GPU, but that's not worth it, because it would be impossible task. So as you might see, these results are pretty great, and I'll not upload these to GitHub. You will not be able to download them, because these files are huge. It's this kind of file takes around 200 megabytes because it has 500,000 records and of many of these metrics, and it takes a lot of time to train. But for you, I'll add my own trained agent that if you are interested, you can run it or you can continue training with it, and you're gonna see all the results. But if you want to train from scratch, it's up to you. I'll add everything on my GitHub and you can go. So that's it about this tutorial. I was really glad that everything worked for me, and I was really happy, and I will be able to move on with this library with some other stuff. And right now I see that my library works a little better than stable baselines because I tested it and I wasn't able to train the bipedal walker hardcore on this environment, but I can do this on this one on my own. And now I could improve the model to work with the model, give it harder architecture, so some more intelligence into the structure, or etc., to learn stuff faster and better. So I'm not doing this. Maybe I'll play around for myself, but I'm not uploading another video about that, but it's up to me and you. So my goal was to give you the code that works, that you can download and etc., share. You can pull the issue if you have any questions and etc., and I'll try to help you out. So that's it about this tutorial. I hope this tutorial was really helpful for you. You're gonna use stuff that I give to you, and if you struggle, leave a comment and we'll solve it. So thank you again for watching. I hope that you watch until then. If you do, don't hesitate to smash the like button. This will help me a lot. Subscribe to my channel, share it with your friends, express your opinion in the comments, and we'll see you next time in another video. Thank you again for watching, and we'll see you next time. Bye.